In this chapter, we'll discuss the chemistry of ethers and epoxides, as well as thiols and sulfides. Ethers are a functional group that contain an oxygen atom surrounded by two carbon chains. A simple example is diethyl ether, which has two ethyl groups surrounding an oxygen. Sulfides are the sulfur version of ethers. They contain a sulfur atom surrounded by two carbon chains. A very simple example is dimethyl sulfide. Thiols are similar to alcohols, except oxygen is replaced by a sulfur. It is typically an SH group bound to a carbon chain. Simple example is methane thiol. Sulfur compounds are well known as having a garlic smell. In fact, many sulfur compounds are found in garlic, mostly sulfides and thiols. Ether, or simply ether, was one of the first general anesthetics used in surgery. However, because of the slow effect on patients as well as the unpleasant recovery, it has been replaced by more modern anesthetics. On this slide, you'll see several examples of general anesthetics as well as local anesthetics. Ethers and sulfides are hydrogen bond acceptors, but they're not capable of donating hydrogen bonds. When mixed with a hydrogen bond donor, such as water, they can accept a hydrogen bond as shown here, but they're not able to donate a hydrogen bond since they do not contain a hydrogen on an oxygen or another electronegative atom. Ethers and sulfides interact with each other through London forces as well as dipole-dipole interactions. In a dipole-dipole interaction, one of the carbons bound to oxygen of an ether would line up next to an oxygen of another ether molecule. Ethers are well-known organic solvents. They're used because of their aprotic polar properties. For example, diethyl ether, anisole, and THF are often used in SN2 reactions. Thiols are capable of hydrogen bonding. However, because sulfur is less electronegative than oxygen, it generally forms weaker hydrogen bonds. As a result, thiols generally have lower boiling points and lower water solubility than similar alcohols. On this table here, you'll see several examples of different functional groups containing different types of intermolecular forces. Alkanes are only able to interact through London forces, so they have a very low boiling point and water solubility. Ethers are capable of interacting through dipole-dipole interactions, so their boiling points are a little bit higher and water solubility is also a little bit higher. Similarly, sulfides are capable of interacting through dipole-dipole interactions as well as London forces. Thiols and alcohols are capable of hydrogen bonding. However, thiols form weaker hydrogen bonds. So you can see here that the boiling point is lower than in a typical alcohol, and so is the water solubility. More acidic than alcohols. Typically, thiols have a pKa of around 10, while most alcohols will have a pKa somewhere around 16. The reason for their high acidity is that when we deprotonate a thiol, we convert it into the conjugate base, which has a negative charge on the sulfur. However, because the sulfur atom is a larger atom than oxygen, that negative charge is spread out more than it would on an oxygen. As a result, the negative charge is more stable when it's on a sulfur atom. That means that the acid that it came from would be more acidic, since the reaction is more likely to happen in the case of a thiol. Ethers and sulfides are not generally considered acids since they do not have an acidic proton on the heteroatom. Ethers are named by giving the alkyl groups in front of the suffix ether. If the alkyl groups are different, they would be given in alphabetical order. If they're identical, then we use the prefix di in front of the alkyl groups. As an example, diethyl ether contains two ethyl groups. In the next example, we have a methyl and an isopropyl group. If we alphabetize those two groups, they would be isopropyl, methyl, followed by the suffix ether. Note that in isopropyl, we use the letter I from the prefix. Most prefixes in naming are ignored when it comes to alphabetizing. So prefixes such as di, tri, tetra, or sec are typically ignored. In the next example, we have an ethyl group and a phenyl group. If we alphabetize those two groups, we have ethyl, phenyl, ether. And then on this last example, we have an allyl group on the left and a vinyl group on the right. If we alphabetize those two, we have allyl, vinyl, ether. Occasionally, an ether group would be attached to a molecule that contains another functional group. And so we would name the ether group as a substituent using the names methoxy, ethoxy, propoxy, or other names. As an example, here we have two methoxy groups on a benzene compound. So we name this as para-dimethoxybenzene. We could also name it as 1,4-dimethoxybenzene. In this last example, we have a terbutoxide group attached to the fourth carbon of this cyclohexene. Note that the double bond is numbered on carbons 1 and 2. That always should be the case. And if we continue in the direction towards the terbutoxide group, the terbutoxide group is on the fourth carbon. To name thiols, we typically give the alkane name followed by the suffix thiol. As an example, we have here ethane thiol. Next, we have cyclohexane thiol. In this next example, we have a thiol group and an ethyl group that are cis to each other on a cyclobutane. So this compound is named as cis-3-ethyl cyclobutane thiol. On the last example, on the top here, we have a thiol that is on a 1, 2, 3, 4 carbon chain. So that would be a butane 1-thiol, since the thiol is on the first carbon on the right. If we continue counting, the fluorine is on the third carbon, so this is named as 3-fluoro-butane 1-thiol. Occasionally, we might need to give the sulfohydryl group as a substituent on a molecule that has another functional group with higher priority. Here is an example. We have this thiol group on the third carbon from the carboxylic acid. Since these are the only two substituents on this benzene, we could also name it with the prefix meta or M. So this compound is named as meta-mercaptobenzoic acid. We could also name it as 3-mercaptobenzoic acid. Sulfides are named very similarly to ethers. We give the alkyl groups in alphabetical order, followed by the suffix sulfide. If the two groups are identical, we would use the term or the prefix di. As an example, we have here dimethyl sulfide. In the next example, we have a methyl group and a phenyl group. Alphabetizing those two groups we would name this as methylphenyl sulfide. If we are going to give the sulfide as a substituent, we can use the term methyl or ethyl and so on. As an example, we have here a methyl on the third carbon of this cyclohexene. Note again that the double bond carbons have to be on carbon 1 and 2. If we number it in this direction as shown, we would come up with the sulfide being attached to carbon 3. As a result, we name this as 3-methyl cyclohexene. In this question, we're going to try to name this ether. Notice we have two isopropyl groups attached to the oxygen. This ether is named as diisopropyl ether since it has two identical isopropyl substituents on the oxygen. In this question, we have a cyclohexane that has both an alcohol and a sulfide. Alcohols are a higher priority group than sulfides, so this compound is named as a cyclohexanol with an ethyl thiol substituent. Notice it is on the third carbon from the alcohol, so this is named as 3-ethyl thiol cyclohexane 1-ol. The most common ways to make ethers is through the Williamson ether synthesis. This is a reaction where we turn an alcohol into an alkoxide by adding base, and then we do a substitution reaction on an alkyl halide. For example, cyclohexanol, when we add sodium hydride, which is a base, the sodium hydride will remove the hydrogen on the alcohol to make an alkoxide ion, which is a much better nucleophile than the alcohol. Then if we add a sterically unhindered alkyl halide, such as methyl iodide, we can do an SN2 reaction where the oxygen attacks the carbon with the leaving group, and as a result, we complete the reaction with an ether. Notice that because this is an SN2 reaction, we want to avoid sterically hindered alkyl halides. So this reaction is best to use primary methyl alkyl halides. Using tertiary or even secondary alkyl halides will often lead to E2 reactions. We also don't want a lot of sterics around the alkoxides for the same reason. In this question, we're going to try to come up with a Williamson synthesis of the following two ethers, methylpropyl ether and anisole. In order to make the following two ethers, we want to think about the Williamson ether synthesis being an SN2 reaction. If we look at the first example, the first question, we have methylpropyl ether, where we have two sterically unhindered alkyl groups around the ether. So that actually gives us two options for answering this question. We can add the methyl group by attaching a bromide, which would mean the alkoxide would have the propyl group. We can reverse that as well, where the propyl group is attached to the halogen, and the alkoxide comes with the methyl group. In the case of anisole, which is methylphenyl ether, we only have one option to make this ether, which would be having a methyl group attached to the halogen, and then the alkoxide would be this phenoxide ion, where the phenyl group is attached to the oxygen. If we try to reverse this, where the phenyl group is attached to the halogen, this reaction will not work since, remember, in an SN2 reaction, the electrophile can't have a phenyl group. The nucleophile would have to get inside of the ring to do an elimination or backside attack. of the halogen. So if we had a halogen here instead of an oxygen, this reaction would not work. In this question, we want to rank the following alkyl halides in terms of reactivity in the Williamson ether synthesis. To answer this question, we want to think back at the requirements for an SN2 reaction, in particular the electrophile. You might recall that the best electrophiles are those that have a good leaving group and also have a sterically unhindered alkyl halide. Looking at the first question, we have bromoethane, which is a primary alkyl halide, which is really good for SN2 reactions. We have 2-bromopropane, which is a secondary alkyl halide, which is not as reactive as a primary alkyl halide. And then we have bromobenzene, which is not a good partner for the SN2 reaction, since the benzene ring will prevent a nucleophile from attacking the backside of the leaving group and eliminating that leaving group. As a result, bromobenzene is the least reactive, bromoethane is the most reactive. In the next question, we have chloroethane, which is a primary alkyl halide, bromoethane, which is also a primary alkyl halide, but it has a better leaving group than chloroethane, and then 1-iodopropene, which is a compound that has a halogen attached directly to the double bond, so it's a vinyl alkyl halide. These are not good for the SN2 reaction. So this 1-iodopropene would be the worst electrophile or least reactive electrophile. Chloroethane would be the next least reactive, and bromoethane would be the most reactive alkyl halide in this group. Another reaction to make ethers is the alkoxymercuration. This typically starts off with an alkene, and we add a mercury reagent plus an alcohol to make an ether. This is very similar to the oxymercuration, which we learned about previously, where an alkene is treated with a mercury reagent plus water to make an alcohol. The reaction that we're about to cover, the alkoxymercuration, works well with primary, secondary, and tertiary alcohols. It starts off with an alkene, for example, styrene. We typically add mercury trifluoroacetate and then an alcohol. So in this case, we're using methanol. That leads to a Markovnikov addition of the alcohol. So the alcohol goes on the more substituted carbon of the double bond. The mercury trifluoroacetate adds to the least substituted carbon. Then sodium borohydride, through a mechanism we won't go into, will replace the mercury with a hydrogen. Overall, this reaction produces the Markovnikov ether from the reaction. Here's a second example with a symmetrical alkene. We're using mercury trifluoroacetate and ethanol, followed by sodium borohydride, produces a ethyl cyclohexyl ether. Notice that in this reaction, we're using mercury trifluoroacetate. This is very similar to the mercury reagent we use with the oxymercuration. In that case, it was mercury diacetate. So in this case, mercury trifluoroacetate simply replaces 3 hydrogens on this carbon with 3 fluorines. Both reagents essentially do the same reaction. This one just happens to work a little bit better, as shown with these examples. Here's another example with an unsymmetrical alkene. We're using mercury trifluoroacetate plus methanol, followed by sodium borohydride to produce the Markovnikov product. Notice the ether attaches to the more substituted carbon. The ether can be predicted just based on the alcohol we're using. So methanol was used here. So we get a methoxy group being added. The mechanism is very similar to the oxymercuration. It starts off with the alkene attacking the mercury, which is a metal. It's electrophilic. The pi electrons in the alkene make it nucleophilic. After the mercury is attacked, one of the trifluoroacetate groups is eliminated. And then at the same time, the d orbital electrons from the mercury attack the developing partial positive charge on this carbon, the more substituted carbon. This produces an mercurium ion. Notice we have seen this before. So this is a three-member ring with mercury as part of the ring, and mercury has a positive charge. It's a very electrophilic ring, so methanol, which is not the best nucleophile, will attack one of these two carbons. Usually it attacks the more substituted carbon. The reason for that is there is more of a partial positive charge on this carbon than there is on the less substituted carbon. So think of this as the bonds between carbon and mercury being partially broken, and that develops a positive charge or a partial positive charge on the carbon here, similar to a more substituted carbocation. There is more of a concentration of a positive charge there, so that is where the methanol adds. In the next step, this hydrogen from the methanol is removed by a base in the reaction. We could use, for example, the trifluoroacetate, which was eliminated in the first step of the mechanism. This leads us to the last intermediate, where a methoxy group has added to the more substituted carbon, and a mercury trifluoroacetate group is on the less substituted carbon. And then lastly, sodium borohydride will replace this mercury group with a hydrogen. This question asks us to prepare an ethyl phenyl ether with phenol using the Williamson ether synthesis as well as the alkoxymercuration reaction. To make ethyl phenyl ether from phenol, we could use the Williamson ether synthesis by adding base, so sodium hydroxide or sodium hydride will do the same thing. The base will deprotonate the hydrogen on the phenol, make it more nucleophilic. And then if we add an ethyl group with a halogen as a leaving group, we can get the ethyl phenyl ether product that we're looking for. Another way we can do this reaction is through the alkoxymercuration reaction, where we use mercury trifluoroacetate and an alkene. If we're trying to add two carbons, our alkene will have to also have two carbons. And then finally, we add sodium borohydride to remove or replace the mercury group that is in the intermediate with a hydrogen. Ethers are a very unreactive functional group. They're very similar to alkanes in that respect. They tend to be stable to bases, nucleophiles, electrophiles, and even mild acids. However, if we treat them with strong acids, such as HI and HBr, so generally we have to use an acid that also has a nucleophilic counter ion, such as a halogen. And if we heat it up, we can cleave the ether in half and produce two products. Generally, we make an alcohol and an alkyl halide. This reaction is generally considered an SN2 reaction, and so the halogen usually adds to the least substituted carbon and then eliminates the rest of the molecules, so starting from the oxygen into an alcohol, in this case an phenol. Here is the mechanism. If we start off with an ether and we add acid, the first thing that happens is the oxygen is protonated by that hydrogen of the acid. That produces this intermediate. This turns an oxygen, which is not a great leaving group, or an OR group that is not a great leaving group, into a much better leaving group by protonating it. The next step involves the counter ion, the conjugate base of our acid, in this case iodine minus, attacking the less substituted carbon. So it goes after the CH2 rather than the CH here, which has a couple of methyl groups. So it goes after the CH2 and then eliminates, starting from the oxygen and everything else attached to it. This is essentially an SN2 reaction, so that is why the iodine prefers to attack the less substituted carbon. That produces isopropanol and iodoethane in this example. In most cases that we do an acid catalyzed cleavage, we usually will observe the halogen attacking the less substituted carbon through an SN2 reaction, as we just saw. However, if we have the opportunity to form a very stable carbocation, such as a tertiary carbon, which is attached to the oxygen, we sometimes observe an SN1 and an E1 reaction instead. Here's an example. We have tert-butyl propyl ether, and we're going to add HBr and heat the reaction. Generally, the first step will involve the oxygen attacking the hydrogen and be protonated. And then that creates the opportunity to form a carbocation, since we have a tertiary carbon next door. So this bond here between the carbon and oxygen, the electrons on it move towards the oxygen. That leaves behind a carbocation, which gets attacked by the bromine to form the more substituted product here through an SN1 reaction. The byproduct will be this alcohol here, which contains the oxygen plus the hydrogen that came from the acid, and then the propyl group. In this question, we want to predict the product from the following reaction. Notice we have a primary, or actually a methyl group, and then on the other side of the ether, we have a tertiary carbon. We're going to add HBr to make this reaction occur. In this example, we have a tertiary carbon plus it is a benzyl carbon. So notice it's on the benzylic position, one carbon removed from the benzene ring. Both of those characteristics make this carbon very likely to be eliminated as a carbocation when we add HBr. So by adding HBr, we eliminate this carbon as a carbocation, which then gets attacked by the bromine to form this product that you see here, the SN1 product. The rest of the molecule, which includes this oxygen, the methyl group, and the hydrogen that was picked up from HBr, will be eliminated as methanol. And then in addition to that, we might observe a small amount of E1 product, and that would be from a carbocation being placed here initially, and then one of the hydrogens on either this methyl group or this methyl group being removed to form a double bond, which you see here. Unlike most ethers, epoxides are a special member of the ether class, which is extremely reactive. Before we get into the reactions of epoxides, let's cover how epoxides are made. Epoxides are three-member cyclic ethers, so they contain two carbons and an oxygen within a three-member ring. One of the ways we can make epoxides is by taking an alkene, adding MCPBA, which stands for metachloroperoxybenzoic acid. It is this molecule here. By adding MCPBA and an alkene, we can produce an epoxide, and it gives us a byproduct of metachlorobenzoic acid. The reaction is said to be a syn addition of the oxygen, in particular this oxygen here from MCPVA. Both bonds between the oxygen and the two carbons that used to be part of the double bond will be added from the same side. Therefore, it is a syn addition of that oxygen. Here is a look at the mechanism. It starts with the double bond attacking the outer oxygen, breaking the peroxide bond. So an oxygen to oxygen single bond is called a peroxide bond. So it's a very weak bond. Those electrons will be shifted here between the oxygen and this carbon. Then the double bond here, one of the pi electrons will be used to pick up this hydrogen, so that hydrogen goes to the oxygen. And then lastly, the electrons from the hydrogen to oxygen bond will be moved to attack the developing carbocation. That essentially leads to forming two bonds between the outer oxygen, so from this electron movement and then the last electron movement, those two bonds are created to the oxygen between two different carbons. And then once again, the byproduct is metachlorobenzoic acid. Another method to make epoxides is through an intermolecular Williamson ether reaction. In order to do this, we have to have a transhalohydrin. In other words, a molecule that has a hydroxyl group and a bromine or chlorine on the adjacent carbon. If we add base, such as sodium hydride or sodium hydroxide, we can remove the protohole, which would make it into a better nucleophile and allow attack on the carbon with the leaving group. That produces the epoxide. Here's a look at the mechanism. Sodium hydride would remove the hydrogen on the alcohol, put a negative charge on the oxygen. That turns the alcohol into an alkoxide. It's a much better nucleophile than an alcohol. Then that oxygen will attack the carbon that has the leaving group through an SN2 reaction and produce the epoxide. Now, you might be familiar with transhalohydrin. We have seen those before, certainly in organic chemistry 1, where we started with an alkene and we added Br2 or Cl2 plus water to produce the transhalohydrin. If we use Br2, we will get a bromine. If we use Cl2, we'll get a chlorine. Notice the product is trans and there are adjacent carbons. Here's another example of using a transhalohydrin to make epoxides. So starting with cyclohexene and adding Cl2 and water, we can make a transhalohydrin, followed by base, sodium hydroxide. It will remove the hydrogen on the alcohol, making a alkoxide, which is a much better nucleophile than the alcohol. The alkoxide will then attack the carbon with the leaving group to form the epoxide. Unlike most ethers, epoxides are extremely reactive. They usually undergo reactions where a nucleophile will open the epoxide ring. If we use a weak nucleophile such as water or an alcohol, generally we need to use an acid to first protonate the epoxide to turn the epoxide into a better electrophile. So for example, if we use this epoxide, we could use sulfuric acid to protonate the oxygen. Then water or an alcohol can add to the more substituted carbon through an SN1 type reaction. The water will generally add from the opposite side of the epoxide ring, so in this case from the bottom, and that is why this alcohol will be at the bottom of the molecule. In the process, any substituent like this methyl group will be inverted in stereochemistry, so it starts as being down, it will finish facing up. In the process, this oxygen from the epoxide will swivel over and become another alcohol with the same stereochemistry as the original epoxide. Here's a closer look at the mechanism for epoxide ring opening under acidic conditions by water. So if we mix sulfuric acid or some other acid and water, we'll make the hydronium ion, which can then protonate the epoxide oxygen. Then we'll have this intermediate, which will be attacked by water. If it's a symmetrical epoxide, it won't matter where the water adds. If it's a unsymmetrical epoxide, water will usually add to the more substituted carbon. In the same step, the bond between carbon and the oxygen will break and the electrons will be sent to the oxygen to eliminate the positive charge on the oxygen. In the next step, water or another base will remove a hydrogen from the water molecule that added to open up the epoxide, and that will result in a trans 1,2 diol. The ring opening of an epoxide should remind you of other reactions we have seen in the past. For example, an alkene reacting with bromine will result in a three-member ring, which we call a bromonium ion, since it has a positive charge on the bromine. This will be attacked by the Br negative, which is the leaving group on Br2 from the first step. That bromine will attack and open up the three-member ring. Similar reactions occur if we use Cl2. That leads to chloronium ion, which will be opened up by a chlorine. And another similar reaction is the oxymercuration or alkoxymercuration, where a mercurium ion involving a three-member ring with mercury having a positive charge, which gets opened by water. Similar to water, alcohols will add to epoxides under acidic conditions. For example, methanol and sulfuric acid will lead to the acid-catalyzed ring opening of this epoxide. Initially, the oxygen of the epoxide will be protonated, and then methanol will add to the more substituted carbon through an SM1 type reaction, leading to this as a product. Notice the methoxy group is added to the more substituted carbon. It will be added from the opposite side as an epoxide ring, so in this case from the bottom. And the methyl group that was originally there will be inverted from being down to being up. And then the oxygen of the epoxide will be turned into an alcohol. Here's a second example. We have an unsymmetrical epoxide. If we add sulfuric acid and sulfuric acid and methanol, the methanol will add to the more substituted carbon, giving this as the product. Halides can also be used to open up epoxides. Hydrogen halides provide both an acid and a nucleophile in the same molecule. Here's an example with a symmetrical epoxide. If we add one of the hydrogen halides, it could be HF, HBr, ACl, or HI. The halogen will add to one of the carbons of the epoxide. It will add from the bottom side since the epoxide was originally up, and then the alcohol will end up on the top since that's where the epoxide oxygen started. As a result, we end up with a trans halohydrin from this reaction. The addition of hydrogen halides to unsymmetrical epoxides, the reaction will change depending on the exact substitution around the carbons of the epoxide. For example, if we have a primary and a secondary carbon, like shown in this first example, the chlorine of ACl will generally add to the least substituted carbon through an SN2 type reaction, giving us this as a product. However, when we involve a tertiary carbon or a secondary benzylic carbon, which are highly stable carbocations, the chlorine will generally add more through an SN1 type reaction, and will add to the more substituted side to give us this as a product. Let's take a look at the SN1 mechanism that we saw on the last slide with involving a tertiary carbon that is attached to an epoxide. Notice in this example, here we have a tertiary carbon, and here we have a secondary carbon in this epoxide. If we add HBr, the first step will be to protonate the oxygen of the epoxide, giving us a protonated epoxide intermediate. We can think of that protonated epoxide intermediate as having a partial bond broken between the oxygen and the carbons that it is attached to. If we think about having a carbocation or a partial positive charge on the tertiary carbon, based on what we know about stability of carbocations, we would say that that's a more stable carbocation than the alternative secondary carbon or carbocation that would form from breaking or partially breaking the bond between this carbon and the oxygen of the epoxide. As a result, the bromine generally tends to add to the more substituted carbon when it comes to an epoxide that has a tertiary carbon or even a secondary carbon that is also benzylic. In this question, we're going to look at two examples of an epoxide ring opening with hydrogen halide, HCl to be exact. We have an example here that has a primary and a secondary carbon. In the second example, we have an epoxide that has a secondary carbon and a tertiary carbon attached to the epoxide. In the first example, we have an epoxide that has a primary carbon and a secondary carbon. When we add HCl, the chlorine will do an SN2 type reaction and add to the primary carbon to give us this trans halohydrin. However, if we have an example where there is a secondary carbon and a tertiary carbon, the reaction will undergo more of an SN1 type reaction, and the chlorine will add to the more substituted carbon, giving us this as a product. Use strong nucleophiles, stronger than water and alcohols. We generally do the reaction under basic conditions. There's no need for an acid since the nucleophile can add directly to the epoxide without needing to protonate the epoxide first. An example of such a nucleophile would be the hydroxide ion, which can come from sodium hydroxide or potassium hydroxide. If we add this to an epoxide, generally the hydroxide will add to the less substituted carbon in an SN2 type reaction. That would give us this alkoxide intermediate, which would be protonated by water or some other proton source to give us a 1,2-diol. If we use the conjugate base of an alcohol, like sodium ethoxide, similar reaction occurs where the nucleophile adds to the least substituted carbon through an SN2 type reaction to give us this alcohol that has an ethoxy substituent on the carbon adjacent to the alcohol. Here's an example with sodium methoxide. It will once again add to the least substituted carbon, giving us a methoxy substituent there. Notice the stereochemistry. It is facing down since the original epoxide was up. The oxygen of the epoxide eventually becomes an alcohol with the same stereochemistry as the epoxide. There are a number of nucleophiles we can use with epoxides, for example, hydrides. So lithium aluminum hydride can provide a hydride to add to the least substituted carbon in an SN2 type reaction. That would result in the more substituted carbon obtaining an alcohol from the epoxide oxygen. Grignard reagents can transfer an alkyl group, such as an ethyl group, to the least substituted carbon, as shown here. An organolithium would do a similar reaction. In this example, we're using a methyl lithium reagent that would transfer a methyl group to the least substituted carbon. Notice in each case, the Grignard and organolithium, the alkyl groups are always added from the opposite side as the epoxide, in this case facing down. The alcohol will always end up on the top side if we start with an epoxide that is facing up. Primary and secondary amines are really good nucleophiles that can add to the least substituted carbon from the opposite side as the epoxide, as shown here. Note that tertiary amines generally are not nucleophilic since they already contain 3 carbon chains. Adding a 4th group from an electrophile would mean that the nitrogen would have a positive charge, and generally this does not occur. We're looking at 3 more nucleophiles. Cyanide can act as a nucleophile to add to an epoxide on the least substituted carbon, as shown here. A thiolate ion can also add to the least substituted carbon through an SN2 type reaction. And an azide would have a negative charge on one of the nitrogens, can also add to the least substituted carbon, as shown in this last example. Epoxides have been used in a number of syntheses throughout the years, including in the synthesis of some beta blockers. Here's an example, starting with this phenol. If we add base and an alkyl halide, we can do an SN2 type reaction where the oxygen attacks this carbon and eliminates the chlorine to attach this carbon chain that contains an epoxide at the end. If we add an amine to that epoxide, it will attack the least substituted carbon to give us our final product. In this question, we're going to try to predict the product from a Grignard reaction on an epoxide. Here we have an epoxide that has a carbon with 1 alkyl group, and this one has 2 alkyl groups, an ethyl and a methyl group. Grignard reagents are generally very strong nucleophiles, so they will prefer to do an SN2 type reaction on epoxides. And they'll add to the least substituted carbon, which is the carbon on the left. As a result, we have now the phenyl substituent on that carbon. The more substituted carbon will obtain an alcohol from the epoxide. In this slide, you'll have a number of questions, problems related to the reactions of epoxides. So I encourage you to try these reactions and try to predict the product from each of them. In the first example, we have an alkyne that has a negative charge. We know that since it's next to the sodium. And that carbon of the alkyne should attack the epoxide as a nucleophile. Notice this is an unsymmetrical epoxide. And you want to look at the possible products from this list on the right and pick the correct one. You try to solve the questions from the last slide. You should hopefully get the correct answers, and you'll be able to answer the question, was the sodium atom certain that he had lost an electron? The answer is on the bottom of this, but you will fill in essentially the letters that correspond to the products that were on the previous slide on the right side. Brown ethers are cyclic polyethers. They're typically named as X crown Y, where X is the total number of atoms in the ring, while Y is the total number of oxygens in the ring. As an example, we have 12 crown 4, which has 12 total atoms, as well as 4 oxygen atoms, and so it is named as 12 crown 4. We also have 15 crown 5, which has 15 atoms, as well as 5 oxygen atoms, and then 18 crown 6 shown here. Each of these crown ethers has a specific size in the cavity inside of the ring, and so it's able to coordinate to different cations, binding specifically to certain size cations. For example, 12 crown 4 can bind selectively lithium. 15 crown 5 ethers can selectively bind sodium. And then 18 crown 6 binds potassium selectively over the other cations, which are smaller. One of the applications of crown ethers is that they are often used as additives in organic reactions to help dissolve certain ionic compounds. As an example, if we wanted to do an SN2 reaction between an alkyl halide, which is organic soluble, and sodium acetate, which is ionic and water soluble, in order to have the two mix well, we often use a crown ether, such as 15 crown 5 ether, which is able to dissolve sodium, and as a result, it will help dissolve the acetate ion into a solution with diethyl ether. And as a result, we can get a effective or productive reaction between sodium acetate and this alkyl halide. Certain natural antibiotics behave similar to crown ethers. Here's an example of nonactin, which is an antibiotic that is able to bind potassium ions selectively over other types of ions. It is an antibiotic because it's able to bind potassium and bring it out of the cells of bacteria by helping potassium cross the hydrophobic cell membrane that the most bacterial cells have. And as a result, it eventually leads to the killing of the bacteria. One of the simplest ways to make thiols is by taking an alkyl halide and adding a thiolate ion. In an SN2 type reaction, the thiolate ion will attack the carbon with the leaving group and do an SN2 reaction to substitute in the thiol. Thiols can undergo a number of reactions. One of them is they can be alkylated. If we take a thiol and add a base like sodium hydroxide or sodium hydride, the base will remove the hydrogen on the thiol, make a thiolate ion, which will then attack an alkyl halide in an SN2 type reaction to give us a sulfide. Here's a look at the mechanism. Sodium hydride will remove this hydrogen, producing a thiolate ion, which will then do an SN2 reaction on a primary alkyl halide to produce the sulfide. This reaction works best when there isn't a lot of sterics around the alkyl halide, so methyl halides, primary alkyl halides, or even sometimes secondary alkyl halides work best. Here's an example with sodium benzene thiolate. It will attack the methyl group that is attached to this iodide to give us methylphenyl sulfide. Thiols can be oxidized with mild oxidizing agents such as hydrogen peroxide to produce disulfides. Disulfides can be converted back to sulfides by using reducing conditions such as a metal and an acid. For example, we can use zinc and HCl to perform this transformation. This is an important reaction, both the forward and backwards reaction in the chemistry of peptides. Disulfides are part of, or they make up disulfide bridges, which are cross links between cysteine amino acids and proteins. Here is a simple look at the reaction. Here's a cysteine amino acid. Cysteines are recognized by the fact that they have a thiol side group. If we add an oxidant, two of these amino acids would link through a disulfide bond. If the amino acids are part of a peptide, then we can link two peptides through this reaction. Bridges are important in the tertiary structure of proteins, along with hydrogen bonds, ionic bonds, and hydrophobic interactions. Looking at this structure, we can see a disulfide bridge, an ionic bond between an ammonium group and a carboxylate group. We can see hydrophobic interactions between different alkyl groups on two different amino acids, and we can see hydrogen bonding between these two amino acids. These interactions help form the tertiary structure of a peptide, as you can see here by this structure. In addition, disulfide bonds are important in the process that we call a perm. In a perm, we generally take the disulfide bonds of keratin, which is the structural protein of hair, and we reduce the disulfide bonds with a reducing agent that will turn the disulfide bonds into thiols. That allows the hair to be molded in the shape that we need. And then after that process, if we add an oxidant like hydrogen peroxide, we can oxidize those thiol groups and back to disulfide bonds. Unlike ethers, sulfides are a little bit more reactive. One of the reactions that they can undergo is an alkylation reaction with an alkyl halide. For example, dimethyl sulfide, when mixed with iodomethane, will undergo an SN2 reaction as shown here. The sulfur will attack the methyl group, eliminate the iodide, and result in a sulfonium salt with the sulfur having a positive charge. Sulfonium salts are stable compounds that are usually used as alkylating agents. In other words, they're used to transfer an alkyl group. For example, this trimethyl sulfonium salt, when mixed with sodium methoxide, will undergo an SN2 reaction where the nucleophile attacks one of the three methyl groups and then eliminates the sulfur and the two methyl groups that are attached to it. As a result, we get a dimethyl ether product as well as a byproduct of dimethyl sulfide. If we start off with an unsymmetrical sulfide, sulfonium salt, the nucleophile, such as sodium ethoxide, will attack the least hinder carbon. In this example, the least hinder carbon is this methyl group. The oxygen will attack that methyl group, eliminate the sulfide that is attached to it. As a result, we get this ethyl methyl ether as well as a sulfide byproduct. The chemistry of the mustard gas chemical agent can be explained by a lot of the reactions we just learned in this section. Mustard gas is a chemical agent that has been used in World War I as well as other conflicts. It is an agent that generates hydrochloric acid and leads to blisters on the skin as well as the lungs of the victim. The way this agent works is by first the sulfur attacking one of the carbons that has a chloride leaving group, forming a sulfonium salt, which then is opened by a water molecule or other nucleophile. This results in an HCl byproduct. The reaction can be repeated again, where the sulfur attacks the other carbon with the chlorine leaving group, forming a sulfonium salt. Water once again attacks the sulfonium salt and forms a final product for the mustard gas, as well as a second molecule of HCl. The essential amino acid methionine is essentially a sulfide which can react with ATP to be alkylated. The sulfur would attack the carbon here that has a triphosphate group, which essentially behaves like a leaving group. As a result, we produce a molecule called SAM, which is in itself is used as an alkylating agent, and specifically the methyl group here is often transferred to different nucleophiles in our bodies. Here's the structure of SAM. SAM is known as a methylating agent. This methyl group here is a good electrophile for different nucleophiles, such as an amino group on noradrenaline. The amino group will attack the methyl group, eliminate the sulfide as well as everything else attached to it, resulting in a methyl group being transferred and producing adrenaline. Sulfides can be oxidized by mild oxidizing agents such as MCPBA or hydrogen peroxide. For example, if we use one equivalent of MCPBA, we can convert a sulfide into a sulfoxide. The reaction starts by one of the lone pairs on the sulfide attacking this oxygen of MCPBA, breaking the peroxide bond to form a double bond here, using the electrons from the carbonyl to pick up a hydrogen and place it on this oxygen. And then lastly, the hydrogen or the electrons between the oxygen-hydrogen bond will attack the sulfur, producing essentially a double bond between sulfur and oxygen. You may encounter another resonance form of sulfoxides, which has a positive charge on sulfur, a single bond between sulfur and oxygen, and a negative charge on the oxygen. Sulfoxides can be oxidized further with a second equivalent of MCPBA or even hydrogen peroxide. They'll be turned into a sulfone. Here's a second example with methylphenyl sulfide. If we use one equivalent of hydrogen peroxide, it'll be oxidized into a sulfoxide. Further oxidation with a second equivalent of MCPBA or hydrogen peroxide will convert it into a sulfone. We'll now review many of the reactions we covered in this chapter. We'll start with this reaction on top, where we have an alcohol. We are going to add base to it, and then methyl bromide. In the second reaction, we have an alkene. We're going to add an alcohol, and then a mercury trifluoroacetate, followed by sodium borohydride. In the next reaction, an ether will be treated with HBr. The fourth reaction will involve an alkene and MCPBA. And then lastly, this trans-halohydrin will be treated with a base, which is sodium hydride. If we take an alcohol and treat it with base, the first thing that will happen is the base will remove the most acidic hydrogen, which is this one here. The resulting alkoxide intermediate will react with an alkylating agent such as methyl bromide to add a methyl group to the oxygen. If we use an alkene and mix it with isopropanol and a mercury trifluoroacetate reagent, this will result in the alcohol adding to the more substituted carbon, and then the mercury trifluoroacetate group adding to the least substituted carbon. Adding sodium borohydride will convert that mercury trifluoroacetate group into a hydrogen, thus giving us this as a product, the Markovnikov product from the alkoxymercuration reaction. If we have an ether and we treat it with HBr, generally the bromine will attack the least substituted carbon through an SN2 type reaction, and the rest of the molecule, starting from the oxygen, will be eliminated as an alcohol. With alkenes, if we add MCPBA, we can convert them into epoxides. A transhalohydrin treated with base will lead to an intramolecular Williamson reaction where that alcohol will be deprotonated, turning it into an alkoxide, a much better nucleophile than the alcohol. That oxygen will then attack this carbon and eliminate the bromine, resulting in an epoxide. In this next question, an epoxide will be treated with sulfuric acid and water. A similar reaction would be taking this epoxide, sulfuric acid, and ethanol. HBr is treated in this third reaction with an epoxide. In the fourth reaction, this epoxide will react with a Grignard. And then lastly, a thiol treated with base, such as sodium hydride, followed by ethyl iodide. When we take an epoxide and we add sulfuric acid and water, generally the water will add to the more substituted carbon. And so the water that adds will add from the opposite side as the epoxide, resulting in this product. The oxygen from the epoxide will be turned into another alcohol, giving us this 1,2-diol. Adding sulfuric acid and ethanol to an epoxide will result in a similar reaction where the alcohol adds to the more substituted carbon. In this case, we'll add an ethoxide substituent at the more substituted carbon from the opposite side as the original epoxide. The least substituted carbon will turn into an alcohol. An epoxide treated with HBr will result in a bromine adding from the least substituted carbon through an SN2 type reaction. A Grignard reagent will also add to the least substituted carbon and result in an alcohol on the more substituted carbon with the same stereochemistry as the original epoxide. In this particular, or with this particular Grignard, we add a methyl group to the least substituted carbon. In the last reaction, we're taking a thiol and adding base to deprotonate the thiol. That turns the thiol into a thiolate ion, which is a better nucleophile, which will react with this carbon, eliminating the iodine and adding an ethyl group on the sulfur. In the first reaction on this slide, we have a thiol, and we're going to add mild oxidizing agent, hydrogen peroxide. In the second reaction, we take a disulfide and add zinc and HCl. In the third reaction, we're taking a sulfide and adding 1 equivalent of MCPBA. In the fourth reaction, we add 2 equivalents of NCPBA. And then in the last reaction, we'll take a sulfide and add a alkylating agent shown here. When we add hydrogen peroxide or another oxidizing agent to a thiol, generally 2 molecules of the thiol will be converted into a symmetrical disulfide. We can reverse that reaction or just simply take another disulfide and add zinc and HCl to reduce the disulfide into 2 molecules of a thiol. Adding 1 equivalent of MCPBA to a sulfide will turn it into a sulfoxide. 2 equivalents of MCPBA will turn a sulfide into a sulfone. Lastly, with sulfides, if we add alkylating agents, the sulfur will attack, in this case, the carbon here with the leaving group to form a sulfonium salt. On this slide, we have a synthesis problem where we start with a alkene, and we're going to turn it into this ketone that has a similar number of carbons, if you see here, and also a phenyl ring attached. Comparing the alkene and the product that we get from this reaction, we probably should be looking at using an epoxide. In other words, turning this alkene into an epoxide and then using some sort of nucleophile to add the benzene ring, and then later on oxidizing the alcohol into a ketone. So the way we would do this is first adding MCPBA to the alkene to turn it into an epoxide, then add an organolithium or a Grignard to that epoxide, which would add to the least substituted carbon through an SN2 type reaction. That would give us this alcohol, which we can oxidize with chromic acid or PCC into a ketone.